Welcome, section 11.2. Keep going with this fun stuff. Now we're talking about circuits in more detail because there's plenty to talk about. Okay, learn and check review questions here. Let's go into these videos. I put them also in the playlist, labeled under 11.2. So if you go to the playlist, you should, in the description, of my playlist, you should see these two videos there. So hopefully that'll help you stay organized with it. Great, so we're going to talk about electric circuits. So what is an electric circuit? It's a closed pathway along which electrons can flow from and return to an energy source, like the example of the battery with a wire being connected to the light bulb, right? So once we've created the full circuit, then electrons flow through and then the light bulb goes on, right? Connecting wires are conductors that join different parts of a circuit together, such as a light bulb, a switch, and an energy source, right, or whatever. Two locations in a cell that must be connected to other components of a circuit are the positive terminal and the negative terminal. So two different things, one positive, one negative that we have to go through when we flow. I think that it might be helpful for me to show you something here. Remember when we went to it's PHET, you can go here to search these letters and it should be the first one. If you go to the physics section of there, you see a whole bunch of different things. Remember we did the balloon with the sweater before? And we can also go to, sorry, I should look this up, circuit construction kit, virtual lab. I think let's maybe go to this one here, circuit construction kit, DC. So we click on this, and then it will bring up this simulation, right? And we can, just go to the lab. Great. I can show you how to use this quickly, and you can play around with it because I'll give you some more things to do. But I wanted to just create a very simple circuit and show you how it worked because this is a great thing because it shows the electrons. So we're going to keep it very simple. We're going to put a battery. We are going to have wires and a light bulb, right? So that's the only thing that's going to be part of our circuit. Okay, now just when using the simulation, we connect wires like this. Maybe I'll do a different a video for this sim if you need one, but it's very straightforward. And then you just drag. So basically everything has 2 points. You notice that, and if I wanted to disconnect something, I click on it and I can click the scissors, which basically cuts the connection. Notice everything is 2 points. There's a circle there, one here, one here, one here, one here, right? There's 2 points on basically everything. So what I do is I connect the wire to the one end of the battery, doesn't matter where, and I connect the other end of the wire to one of these circles on the bulb, and it automatically connects. Now notice how these are black now as opposed to red, right? Again, I connect this wire to this end of the battery and it goes black, which means that the connection is successful. But hey, the light bulb's not on yet, right? What you notice is I've just added a bunch of wires just to make this look more like a typical diagram that you would draw. You notice that in real life it's not as neat and tidy. So if you're like me and you need things to be organized, then this can help. So you saw me just add these extra wires on, but think of this as just one continuous wire. Now let's actually connect these things. So again, we'll connect this one to the one end of the battery, and now let's see what happens when we connect to the light bulb. Aha! We see that the light bulb has these rays of light, and then notice these little negative these little negative circles. What are they? They are electrons. We can see the electrons moving through the circuit, right? So the 2 terminals on either side of the battery, positive, negative, and then we see electrons actually moving through them. Okay, so this is a nifty little diagram that will hopefully help visualize what's going on when we talk about these circuits. Okay, we need that to happen and we need it to be a closed circuit because if it is not closed, it will not work, right? If we were to add a switch to the situation, if the switch is open, right, nothing happens. But if I close the switch, aha, then we see that the light is now back on, okay? Let's talk about that in a bit more detail because that's going to be very important. Back to our slide. So what is a switch? A switch is a control device made of conducting material that can complete or break the circuit to which it is connected. Okay, so they're useful, right? They're added in on purpose. Electrons will not flow through a circuit where there is a break or a gap, right? Because remember that electrons are physical things. They're made of matter, or they are matter. They make up matter. So they need to actually have something that's touching, right, in order for them to flow through. You can get sparks or you can get lightning. But what do we know about lightning and about shocks or sparks, right? They don't last very long because it's a whole bunch of electrons moving very, very fast. But once the charge differential, right, in the case of lightning, once the static electricity has been, once there's no more static electricity, there's no more need to flow, right? Because the charges have been balanced again. Remember that what we're doing with our electric circuits is the battery or the cell is providing sort of like a push to push the electrons. So it's different, right? It's not like a charge. I know that you might think that there's a charge with this positive and negative, but ultimately we're basically pushing the electrons through this circuit. All of this stuff, very, very complicated, right? So bear with me on this, and if you have questions, please don't hesitate to let me know, okay? All right, open switch or a loose bulb, for example, anything, or like a cut wire, a damaged wire, those things can all stop a circuit from working, right? And we see that we have our open versus closed. Now, this is the terminology that's going to be really important. Notice that when I'm saying in open circuit, which of these two, I know it says down here, but if you look at these two guys, the open versus closed circuit, remember that an open circuit means that the circuit has a break or a gap, or the switch is open, right? Like a drawbridge is open, it's up, right? Nothing can flow through. Versus a closed circuit, like over here, which means that the switch is down or there's no breaks, things can flow through. Now this is very, very different than how we say, hey, can you turn the light on versus the light off, right? I don't know how you guys say it. Some people say, can you close the light? You know what I mean? Maybe if you're one of those people, I am not. But we have different terminologies, right? The light's either on or off. And so that might be a bit easy, right? Because we see light on, light off, that's easy to identify. But the terminology that we need to connect there is that light on, closed, right? Light off, open. So this is really tricky for some people, because if you say close the light, you mean turn the light off, right? If you've heard that phrase before. If you haven't, then just please ignore me. But I feel like statistically there's 50 of you. Then some of you probably say this. And that's really challenging for a lot of people, right? Like you get the idea, but I think it's just making that connection in your head so that on a test or a quiz, if we have, I don't know. But in the future, if you encounter this stuff, then I don't want you to get too mixed up with that, okay? So that's just a tricky one. So just point that out about this slide. There's a bit of a trickiness to it. Now, how do electrons move? Remember that we cause charges to separate. Excess electrons builds up at the negative electrode. The other has a deficit, which is called the positive. And then there's a charge separation, which basically creates an electric field, which pushes electrons to move in a singular direction, right? Difficult stuff. But what we're going to do is, for our purposes of grade 9, we're going to say that electrons in the circuit are going to go from the negative terminal of the cell or battery to the positive terminal, right? That's nice and easy to picture, because you could say, oh, the negative terminal is negative because there's a bunch of electrons there, and they go towards the positive side, right? It's tempting to think of it like, if you want to picture it like, oh, it's just like the charge attraction. That's okay, but it's not what's exactly happening, right? If you go into be an electrician or go into electrical engineering or something like that, then you're going to come back to me and say, sir, this is all wrong. Remember, because electricians, electrical engineers, people that work with electrical equipment, they often have their own ways of measuring these things. And like we said before, that positive and negative, those charges, we made them up. Humans made them up. They are arbitrary. So the same thing sort of applies to this motion of electrons. It's very complicated. Maybe some of you have people in your families that work with this, and so you might know, or maybe you are into electronics, and you might know this already yourself. But if you don't, please don't worry. It's just grade 9. At this level, basically, all you need to know is that electrons go in only one direction. And that is the important thing, is that all the electrons move in the exact same way. It's a one-way street on that wire. All the electrons go to the same place. So here's just a little diagram down here. It can be a bit misleading. It's copper colored because this is supposed to be copper metal. This is like a zoom in on the wire, right? So the wire here is just like a black line, but it's supposed to be copper conducting electrons. And we see that these little positives are the nuclei of the copper atoms, and the electrons basically move through them, right? all in one motion from negative to the positive, right, through these wires. That's the important thing. Okay, let's talk about charge and current. I can't remember if we've mentioned current. Oh, no, yeah, current electricity. Well, current electricity gets its name from this concept called current, okay? So one thing is called electric charge, right, is passing point in circuit measured in terms of a large number of electrons, right? So we use this unit of charge. So each electron basically has like one unit of charge, right? It is one negative charge for an electron. But remember that electrons are really, 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 really small, right? And remember that there's also billions and billions of them. So in order for us humans, us large humans, to be able to make any use of these things, we have to do a slight conversion in order to get numbers that will work with us, right? So the voltages and stuff on your batteries or on light bulbs or the wattage of light bulbs, all those sort of like characteristics are based off of the idea that these electrons, these negative charges, are moving. But because there's so many of them and the charge is relatively small, we have to sort of scale it up, if that kind of makes sense. We call the charge given to a whole bunch of electrons a coulomb, right, named after a scientist. It has the symbol C, right? And we say that by definition that 1 coulomb, okay, of charge is how much charge is possessed by this many electrons, right? 6.25 times 10 to the power of 18. So this is basically the number 625 followed by 16 zeros after it, okay? It's a very, very large number because there's lots of electrons, right? Okay, so if you picture it like this, like all these little electrons individually have a tiny charge. If we put like billions and billions of them together, they're all going to have more charge, right? Like we talked about with our electric field. So if we were to somehow like put all these electrons together, right, in one little space, this particular number would have 1 coulomb of charge. And then this gives it, the reason we do this is just so that we can do more scaled up math and stuff, so that we don't have to be using really, really large numbers, so that we can say, oh, this is like 5 watts, or the voltage is 120 volts, instead of saying, oh, it's 120 billion volts, right? Like that's why we do it. It's just so we're not using these ridiculously big numbers. We want to use numbers that aren't quite so big. So we factor the big number into our definition itself. Let this sink a little bit. Please don't overthink it. Basically, what I need you to think about is that this concept of charge that we were talking about, its unit is called a coulomb, right? And we use the symbol C for those units going forward. Okay, let's talk about what electric current is. I'll make some supplementary stuff for this, maybe a supplementary page or something just for more of this info. You might have to watch this video a few times, or maybe find whatever you want to do, but this is tricky stuff. So some review of this will be helpful, and read the textbook too, because it will also help it, right? So an electric current has the symbol I, right? Because this is like just like a concept there, and with sort of the property, which is current, and it's being measured in this thing called ampere, the unit, right? So what is current, right? It's the rate of movement of electric charge. Okay, so we said that electrons were moving, right? Electrons are moving through a wire. We know that electrons have charge, and we know that there's a whole bunch of them. Remember that electrons move really, really fast too, right? Don't forget that. So they're moving through insanely fast. So this many electrons doesn't take that long to move through wires, right? So we want to talk about what rate, how much of this charge is passing a particular point, and we refer to that as current. If you want to just picture like a river, right, with water flowing through it, and that will also have a current, it's a very similar analogy, is that if I'm looking at a river, I want to know how much water is passing through it at a particular point, right? That's sort of like how fast the river is moving. Also remembering that we're not talking about like a cup of water. We're talking about like thousands of gallons of water or whatever in a river, right? For example. So there's tons of water moving through, but we use this term current. Oh, let's just see how fast it, right? So hopefully you see the analogy there, that we're not talking about small amounts of water, we're talking about large amounts of water, but we're using this term to refer to all of the water so that it makes a bit more sense for us, right? So that when I go swimming in the river, I know about the current, if that helps. Okay, so current results from the flow of electrons. We use amperes, capital A, to measure this concept. That's called current. And then we use an ammeter. There's a little picture of it down here. It's input, output for the ammeter. We can find out how much current devices have, right? All electric devices have current in them. And then a current of 1 amp in a circuit means that 1 coulomb of charge passes a given point in the circuit every second. And we have this little equation showing the relationship between Q, the charge, divided by the unit, the lowercase t, which stands for like time, right? So charge divided by time will give us the current. Confused yet? Hopefully not. I'm going to keep going with this video, and I can just add stuff after. Maybe if people say, sir, I'm completely lost, I can help you with it later on. But let's just keep going. Let's talk about electrical resistance now, another quantity that we're going to be that applies to electricity. Resistance is a property of a substance that hinders electric current and converts electrical energy into other forms of energy. Resistance is necessary. All things have resistance, and we put it into circuits on purpose sometimes. Okay, so it's caused by metal ions in a conductor that hinder the flow of electrons through the circuit. Because remember that these are physical things. So electrons are moving between copper atoms. There's other electrons. There's lots of kind of situations in there that might hinder or slow down how fast they can move through this, right? So basically resistance is kind of slowing down current, more or less. So in a circuit, a resistor is a device used in an electric circuit to decrease the current through a component by a specific amount, right? Because you need them, right? You need certain currents at certain points in a circuit, and so you can add these resistors to reduce the current as is needed. The unit of electrical resistance is called the ohm, again named after a scientist, right? So here's a little diagram. Picture like a ball, or like this is like the Plinko thing, you know, as the ball would normally just roll straight down the ramp, but these little wooden pegs are in the way. So what happens? The ball rolls down, collides with the first peg, goes in a different direction, hits another peg, you know, and it bounces randomly until it gets to the bottom. And this is a way that we can picture resistance, right? These little pegs are things that slow down the ball's progress, right? So the more pegs we have, the more resistance there is, if you want to picture it. So we have the property called resistance, and we have the unit called the ohm. Just like we have the property of charge, which is Q, and then the unit of coulombs, which is C, as well as the property of current, letter I, and the unit amperes. That's going to be clear when we talk about more of these equations. Okay, let's talk about what a load is. A resistor or any other device that transforms electrical energy into heat, motion, sound, or light. Okay, so we refer to that as a load. Remember, we said that resistors will change the electric energy into another form of energy. Sometimes we want that to happen, right? Well, not sometimes, all the time. What's the point of having all that electrical energy in your phone if it doesn't light up, if it doesn't play sound, right? Light and sound are other forms of energy. So you're basically taking the energy that's stored in the electrons in that battery, and you're converting it into light and sound when you show your friend that YouTube video on your phone, right? That's what's happening. Now, the things in a circuit that do that are called loads, right? So we mentioned resistors are a type of load because they change the electrical energy into something else, right? We have also other examples like fans, ovens, motors, light bulbs, or doorbells, right? All of those things that we put into a circuit are loads, right? Because they're doing something or they're using up energy in some way, right? And we see the different types of energy. So a fan moves around, call that mechanical. Oven, obviously thermal because it gets hot. Motor is mechanical because it moves, but don't forget motor is also going to generate thermal energy, right? A light bulb will create light, also going to create thermal energy, as well as the doorbell will create sound, right? And also a little bit of thermal. In case you can't sort of take my hint, everything will also convert energy into heat, right? That's referred to as loss because these devices are not super efficient, right? The energy that you lose so electrical energy that's lost to heat, unless it's an oven where you want it to be hot, but like a car engine, you don't necessarily want to overheat, so you have to cool it down, right? So using all that energy is going to heat it up, which can be a bad thing. So we often have to add coolant to a car engine to keep it cold, right? So you notice that it's inefficient. If we right, we have no other way of getting around it. We try and make these processes as efficient as we can, but we don't always succeed because what's called like the laws of thermodynamics, right? Just these physical laws that say that anytime you make energy, like it's going to create some sort of inefficiency, right? It's impossible to make a perfectly efficient system. Nothing can be 100% efficient. And the loss, the energy that is lost, is usually in the form of heat. Now, another example of electrical loss, just kind of what we're talking about, is power lines. There have been close to like really high energy power lines, and what do you hear when you need them? You hear buzzing, right? Have you ever heard of buzzing? You hear something that's also inefficient. That's energy, that's sound energy being created, but it's a byproduct of what we want those power lines to do. So there's so much power in them that they're losing some of that energy to sound, which isn't good, which is inefficient, because it ultimately means that when my house needs all its electricity, I'm taking electricity through these power lines, but I'm not getting it's not matching the output from the power plant, right? I need to have a little bit extra because of the energy that's being lost there, right? So you see how that works, right? Sort of like we're losing stuff as we go through. So basically, as we're transferring energy from one location to another, we're sort of losing little bits of energy along the way. Just like if you're carrying like your groceries to your car and like you're dropping them on the way to the car. I guess I don't know why you're carrying your groceries. Anyways, hopefully you sort of get what I'm saying there. Okay, and let's talk about another property that's called potential difference. This is probably the hardest to understand. I feel like resistance is not too bad. It slows things down. Current is just like the speed, whereas the potential difference is a very, very tricky concept to get your head around. I still have trouble with it, so please don't feel bad if you do also. And remember, this is just grade 9 for now, so whatever helps you sort of get this kind of concept down will be good. But if you're taking more sciences later on, you will have to adapt this or revise this at some point, right? So please just kind of bear in mind that I'm trying to do my best to explain this to you in a way that's factual, but also I'm trying to make sure that it's a way that is accessible to everybody. Okay, so let's talk about difference. So we have different sizes of batteries, like we talked about, because it's chemical in nature, and we get different electric charges that move through. So we have, our AAAs, AA's, D-cell batteries, and they're marked with this thing 1.5 V volts, right? You probably have heard this term volt before. It's related to the amount of energy that is provided to each coulomb of charge that moves through a circuit, right? So potential difference, which is also called this term voltage, right? They mean the same thing. So if I say potential difference or if I say voltage, those are synonyms. They're connected with energy ultimately, okay? And we can also call this electric potential energy, right? The amount, like sort of how much energy is stored in an amount of charge is called electric potential energy, right? It's called potential energy because it can do stuff, right? Your phone, when it's off, has the potential to light up and play sound, right? But it's not doing that right now. So there's sort of two forms of energy. Either it's sort of not doing, it's waiting, or it's doing the thing. So potential, and then more or less kinetic is the other, is the moving or doing thing. But let's focus on the potential, because that's what voltage connects to. So the cells have different quantities of materials, but there's no difference in the amount of electric potential energy that they provide. So if you look at those different batteries, they're different sizes. They have different stuff sort of in them, but if they all have the same voltage rating, that means that they all supply the same amount of energy. Okay, so when electric charge flows through a light bulb, it enters the filament with a certain amount of energy and exits with a little less, right? That kind of makes sense. When you start a race or when you start running, you have more energy than at the end of the race or when you're done running, right? You get tired towards the end. It's kind of similar here. Not that electrons get tired, but basically an electron will start off with a certain amount, but then when it goes through the light bulb filament, what's happening? We're converting that electrical energy into something else. So the electron will have a little less energy at the end, right? Once it's sort of provided the energy to the light bulb. This loss in energy that it experiences is referred to as a potential difference, right? Or it's the difference in potential energy between the 2 points. Now, all the energy that is lost, or all the light energy and heat energy that comes off the light bulb, will make up that missing amount of energy that comes, that missing amount of electric potential energy, okay? So what we refer to as the potential difference is the difference between the electric potential energy per unit of charge between 2 points in the circuit, okay? If we even forget the unit of charge aspect, you can just say it's just the difference between electrical potential energy between 2 points in our circuit. That's the really important part of this. Notice that it uses the term difference in that you need 2 values, right? A singular value doesn't have any meaning by itself. You have to compare it to something else, okay? Where's my waterfall? Let me just look up good old-fashioned waterfall real quick as I go through, because this is the thing that I use all the time. Oh, this is nice. 3-hour video of large waterfall. That sounds quite nice. Okay, waterfall. Water at the top of the mountain has more energy, right? It has a lot of potential energy because it's just sitting up there. And then the water falls down, right? And then releases all that energy and then smashes into the rocks at the bottom, right? This is a great analogy for potential difference. If I want to kind of look at the energy that the water has, I compare its starting point and I can maybe compare its kind of finishing point, its end point, and I look at the difference of those 2 things, and then I know the total amount of energy that the water had. But you notice that there's kind of 2 moments. When the water is waiting at the top, right, versus when the water is moving down. Now, another way to think about it, the water is already at the top, okay? It is releasing energy as it falls down, right? How would I get that water back to the top? Well, I'd have to put water in a bucket and I'd have to climb, and then I'd dump the water in the top and then it can fall down again, right? What that is doing is like creating the cycle. Notice though that like a ball on the top of your stairs or water, whatever, gravity is the thing that is going to pull it down, right? So you don't really need any energy. It can release energy by falling down, right? So this is called gravitational potential energy. It's no longer potential. Once it's moving, that's called kinetic energy, right? So we've changed the form of the energy, and there's also going to be sound, right? Because waterfalls are loud, and then it's going to hit the ground and then create like spray. So we're losing all this energy as it goes down. But if I took the difference between the top and the bottom, I could figure out how much energy the water had total, right? And then if I wanted to bring the water back to the top, I would have to do some work. I would have to now use my energy to replenish the supply, right? Obviously, now how water gets to the top is like rainfall, natural processes. That's too complicated. I just want to try and get like nice and simple. Just picture basically like water or a ball falling from the top to the bottom. And then let's say it's like a tennis ball. If I were to pick up the tennis ball on the bottom, I'd have to walk it back up to the top and then do it again, or like going down a slide. Hopefully you can sort of picture some of this analogy that we're looking at, right? Potential difference is kind of similar to this. I have to measure 2 points, right, in order to see how much energy is being released. And obviously some waterfalls are bigger than others. So me pouring a cup of water on the sidewalk from not very high up, not a lot of energy kind of coming out there, right? Versus like this waterfall here is massive, lots of energy kind of being released there. So I have to, it's relative to the 2 points, if that makes sense. So the higher up I bring something, the more potential energy it has. But if it only, so like if I go to the top of the CN Tower, right, and I jump down 1 step, right, I'm at the top of the CN Tower, but I've only jumped down 1 step. I haven't released any of that energy. So it's relative to 2 points. That's important there. Hopefully, I'm trying my best here, guys. Hopefully that's okay. And let's talk about this a bit more, because like I said, the potential difference is a difficult concept. Voltage can't be measured at a single point, like I said. It's a measure of the difference between 2 points. Okay, so we're going to do a bunch of units that are going to be combining. So electric potential energy is measured in joules. All right, so that's one sort of thing. Electric charge is measured in coulombs, like we said. And we define the potential difference as sort of combining these 2 ideas, energy and charge. And that's why we have this new concept that's called potential difference, right? So at its core, the potential difference is looking at energy, but it's also looking at energy based off of how much charge there is. So we give it this special name, potential difference, because if we're talking about energy, but we're talking about energy and charge, so hence we combine them, right? Just like our current is sort of a newer term where we're looking at charge and time, right? So we're sort of combining these properties and we're making sort of a new property with it, if that makes sense. So divide the energy by the charge and you will get the potential difference. So what are the units? It's joules per coulomb. That's really confusing, so let's just call it a volt. We give it the special name. This is also Alessandro Volta, which we mentioned last lesson. That's where we get the term volt from. So he also has voltaic cells, but he also gets this term volt sort of in general. And then we measure potential difference with a voltmeter. So current was measured with an ammeter, potential difference measured with a voltmeter. And then we have the thing called a multimeter, which is basically just all like a voltmeter and ammeter all rolled into one. You can measure resistance with it too. You can measure a whole bunch of different things. So these are called multimeters. So realistically, if you've ever had an electrician come to your house, or if you've seen one of these are a lot more practical than having to connect a voltmeter or ammeter at different points in a circuit, let's say in a house. Like if you're trying to rewire a house or something, you're going to use one of these guys, right? You have noticed like two leads, right? Sort of input, output, positive, negative, whatever you want to picture. And then the electrons sort of flow through here and out the other path back into the circuit. And depending on the setting, it will tell you, okay, what's the voltage, what's the current, you know? It'll tell you those things. Alrighty, big lesson, really hard lesson. Pause as much as you need to. Summary chart right here for the different properties that we looked at. We looked at charge, current, potential difference or voltage, and then resistance. Take a look at this table, go through, we have a bunch of different analogies. Electric charge is like the number of water droplets that there are, right? The current is how many water droplets moving past a particular point, right? So you can see that a big tank with a very small pipe will have a sort of slower current than the same tank with a larger pipe, right? More water moves through the larger pipe, makes sense. Potential difference, like we said, is the height from which the water falls, right? So again, same amount of water in both cases. If it's only falling like 1 meter, that's very different than it falling 10. So hence, this water tank on the right has more energy or a greater potential difference than this guy does, right? And then the resistance is like all the obstacles that are stopping the water from flowing, right? So if we have no obstacles, there's no resistance, everything is great, but we might have some blockages in here, right? Think about like a toilet getting blocked, water can't flow through, it is experiencing resistance. Electricity and water are great connections to make, and it's a really, really good analogy because water has to flow through a pipe, right? And you need to have water has to come from somewhere and it has to go somewhere. If it doesn't, then your house is going to get flooded. Electricity works the same way, except if one of those things is disconnected, then it just won't flow, right? So fortunately, that's good so that you don't get like a bunch of electricity, I guess, stuck in your house. But that's why the water analogy works very well, right? And it can help us sort of visualize the electrons as they move through these circuits, right? So we'll probably be using the water analogy a lot more. Okay, that's it for now. Really tough lesson. Hope it wasn't too bad. We'll talk to you guys soon.